And next, let's check how you did analyzing this pattern and analyzing this data. So hopefully you found that what they needed to do was increase their price, because here's where they started, $2.50 per muffin, making $312. If they dropped their price, they would sell more muffins, but the loss of income for selling them more cheaply offsets that. So they would actually make less money. If they increase their price, so $2.75 to $3, $3.25, and so on, you'll find that the revenue actually goes up. So even though they're selling fewer muffins, the muffins they are selling are being sold at a higher price, and that's offsetting the loss of the number of muffins sold. And so with quadratic patterns, you kind of have this tug of war. And when you make a graph, you'll find that it has a curving line like this. And so you can kind of think of there as being a tug of war between the price made per muffin and the number of muffins sold. So as one thing goes up, the other thing goes down, but it's not proportional. This isn't a linear relationship. So there's sort of a tug of war going on. And at that high point, one aspect loses and another aspect wins in regards to which one is having a greater effect on, in this case, the total income. So hopefully you found that the sweet spot was right here, $3.25. They would make $328 total in a week for selling them at that price. And so this is definitely nonlinear. A couple other things I wanted to point out in the pattern is that, first of all, remember first and second differences. Each type of pattern has its own characteristic. This one, actually, let me back up. So with linear, remember, if all of your changes in x were the same, then all of your changes in y were constant. Always had the same amount of change in y for every unit change in x. For exponential, it was a multiplier. So it'd go double, 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 or triple and triple and triple, or cut in half, cut in half, cut in half. So there's always a constant multiplier that was increasing or decreasing the y value for every change in the value of x. Quadratic is definitely more complicated. So for example, going from 299.25 to 312.50, if they increase their price from 225 to 250, they increase their weekly revenue by $13.25. If they increase it by another 25 cents, so from 250 to 275, their revenue would go from 312 to 321, and so that's an increase of 9.25. So notice the next increase of 25 cents, starting at 225, has a smaller effect on their total income for that week than the first change of 25 cents. They increase it by 25 cents again to $3. The increase in revenue is only $5.25, and the next one, $3 to $3.25, they only change their income by $1, and it tops out somewhere around there. And maybe some of you who are super detail oriented actually tried to find a price in between those 25-cent increments to try and figure out maybe more precisely where that high point is in this one, where the sweet spot is in the price. And then if they keep increasing their price, they start losing money. So if they go from 325 to 350, they lose money. They lose a little bit of money the first time, but you can imagine looking at that pattern that as they increase their price by another 25 cents, another 25 cents, the loss of the number of muffins sold is going to have a bigger and bigger effect because they're losing muffins sold at a higher and higher price. And so that effect takes over. Whereas if they decrease their price from 325 and lower, it's sort of the flip side of that happens. As they're selling more and more muffins, they're selling more and more at a smaller amount of money. And it's the selling them at a lower amount of money has a bigger and bigger effect on their overall income. So the tug of war kind of goes the other way as far as which one has the greater effect on income. Needless to say, these quadratic patterns are definitely complicated compared to what we've seen. They're definitely getting a bit more complicated. But there's our sweet spot, somewhere around $3.25 is about the highest they're going to make. On either side of that, they'll lose money compared to what they could be making. It's less than optimal, I should say. They'd still be making income, it's just not the optimal income. So hopefully you tried to write an equation to predict the revenue based on muffin price. So you could just put in muffin price and predict what their income would be. And hopefully you found that it's actually really, really tough. This is supposed to be a difficult problem. So don't get too bogged down in the details as I go through this. We're just getting an idea of what some of the characteristics of quadratic patterns are and what some of the equation forms are, what the graphs might look like, and so on and so forth. So with this one, remember, if you're trying to calculate their income, so here's their income for the week. If you wanted to find their income, you'd multiply the number of muffins by the price of each muffin. Pretty straightforward. But the hard thing is the number of muffins can change, and when you change the price of the muffin, that also changes the number of muffins sold. So it's almost like you have too many variables. So to start getting an idea of what this might look like, you'd say, well, I know I'm predicting the number of muffins by taking that 125 muffins we were talking about and subtracting some number of muffins whenever the price of the muffin increases. So then you've got your price. Let's see, I believe our initial price was $2.50. $2.50. I'm just using N and M as sort of generic variables. So what this equation says, the amount of money earned depends on the number of muffins sold and what the price of each muffin is. But when you increase the price of your muffin by some amount, you decrease the number of muffins sold by some amount. And notice what we now have here is too many variables. That's one of those characteristics where you might get an idea that you're dealing with a quadratic type pattern is when you seem to have too many variables. So one way around this, I've seen a lot of, unfortunately, this is always a really good discussion day when we actually have class. A lot of students come up with a lot of different ways of trying to predict it. One way that some students have predicted it in the past is actually create a new variable. So let's say X, instead of it being the price, let's say X is just a number of 25-cent price adjustments, adjusting up or adjusting down once or twice or three times by 25 cents. And the reason is because that's how the data is presented. If you change the price by 25 cents, you change the muffins sold by 8. So if we define one variable as a number of price adjustments, we can actually turn this into a nice two-variable equation. Well, it's a little bit of a messy two-variable equation. So this time you can say, well, we've got 125 muffins, and we take away 8 muffins every time we adjust the price once by 25 cents. The price of our muffin goes up by 25 cents. So notice now we actually have two variables. We have our y variable is our income. Our x variable is price adjustment. What this one says is if we, starting at $2.50, if we increase by one price adjustment of 25 cents, over here, our number of muffins goes down by 8 for each time we increase it or decrease it by 25 cents. But again, not simple at all. Another way I've seen students do this is they said, well, what if the price was 0? How many muffins would we sell? That would be your y-intercept. So you could back your way up to your y-intercept, and you could say, well, my number of muffins, what you find is 205. So that's how many muffins that pattern would predict you would sell if you lowered your price all the way down to 0. Minus 32 times x. So it's 32 times x. X this time is dollars. And so think if you change the price by 25 cents, and that changes the number of muffins sold by 8. If you change the price by $1, you change the number of muffins sold by 32. So this involves basically using a linear pattern to write an equation for the number of muffins sold, finding what the y-intercept is, and using the slope, so kind of using the slope-intercept form. Notice that's what this is. So there's a slope-intercept form that predicts how many muffins you sell, and the price that you're selling those muffins at is still X. If this is freaking you out, if this is kind of making you a little uneasy, if you aren't able to get this and if this is a little bit foggy, again, this is a mucking about problem. Don't worry about it. You know, we've done problems like that before in class where I show you some really complex algorithms and complex thinking just to get you a general feel for a certain level of complexity of a concept. So hopefully at least we've accomplished that. Don't worry too much if you're having a little bit of a hard time with these equations, but you're going to recognize these forms of equations later on when we look at more quadratics over the rest of our school year. This is the last topic we're going to cover. So to summarize, just talking about differences between quadratic change and the ones that we've looked at before, one of the key differences is that we have a positive and a negative change section in a single function. So with linear and exponential, it either always goes up or always goes down as x increases. With parabola, or sorry, I should say with quadratic functions, you have both in the same function. Part of it goes up, part of it goes down. The shape of it is called parabolic, so you get a parabola. So it's a parabolic curve. We call that a parabola. And a parabola has symmetry. So it has one side that has positive change, one side that has negative change, and it's symmetrical. It also has a higher low point. Which again, exponential and linear patterns don't have. They either keep going up, they keep going down, they don't top out or bottom out at any point. They always go up or they always go down. And finally, if you were to take your graph and keep drawing that curve, you'll notice if it's going to do this shape, notice this graph has two x-intercepts and a y-intercept. And don't worry about the fact that it's kind of sloppily drawn. It should be more symmetrical than that. But one of the other characteristics that we have is there are multiple intercepts. So there are two x's and one y intercept possible. And to make things more complicated, you can have quadratic patterns and parabolas that have no x-intercepts. You can have one x-intercept. You can have two x-intercepts. And you always have one y-intercept, and sometimes the y-intercept is the origin. So there's a lot of stuff going on with parabolas. It's almost like you have a three-dimensional thing. And like I was saying before, it's like you have three variables. It feels like it's not just